Okay, everybody. Today's video 4 of 10 in the countability series. We'll be talking about the idea of functions as relations. It's an alternative viewpoint to the way Coq sees them. Okay, let's get started. So in Coq, you define a function using definition, fixed point, fun, fix, right? All of these at core, the core idea that we see is a function is computational, right? It's all defined as like a process that you run, right? This is, I think, very natural. Coq is a programming language, right? Of course, its functions are just programs that you run. This is not a surprising structure for how Coq does it. But in mathematics, especially in formal mathematics, people take different viewpoints on what a function is. So in math, a function is a special relation, right? It's just a thing that exists. Maybe it's computable, maybe not. It just depends. There's all kinds of functions that it will not be computable. So for example, there's a function f of t equals the number of footsteps on the moon at time t, where t is just time in the universe. By moon, I mean the Earth's moon. And this is a function that's not computable because we just don't know the answer, right? We don't know what it is. We wouldn't know how to compute it sort of far back in time. You need some very precise data to be able to say it. It's maybe a thing you could make computable if we had sort of very second by second information about every footstep that Neil Armstrong took on the moon or Buzz Aldrin. But this is not a function we can just write down. Whereas in math, this is a perfectly good function one can talk about and think about because it's a thing that exists. And we just have to sort of respect the fact that we don't always know what everything does here. Okay, so that's a very high-level sort of philosophical overview of what's going on here. Let's take a break from the philosophical and think about things more concretely. So what we're going to do is we're going to say a function is going to be a special kind of relation. So f, I'm going to write lowercase f, a relation on a times b is a function when, okay, now there's two criteria. For all a in a, there exists a b such that AB is in F, right? This is the idea that there everything in A maps to some B. Now notice that existential means that there could be more than one, right? So we could have, a function where A mapped to two different things. Okay, that seems bad. So the other thing is, 2, F is deterministic. That is, for all A, B1, B2, A, B1 in F, and A, B2 in F implies B1 equals B2. Okay. Put another way, for all A in A, there exists a unique B, AB, in F. Okay, that's just combining those two criteria. Once we have these two criteria, that sort of justifies saying, okay, f of A is equal to the unique b such that ab is an f, right? So that's just, we'll use this notation to mean precisely that b. Okay, let's look at some concrete examples. Okay, so I'm going to write the function down, and what I recommend you do is take the video slowly. I'm not going to say what the function is, and I want you to try to guess what it is as I'm writing it down. So here, I'll name them each in turn. So this will be, we'll call this function g. Bool to bool. Okay, what function is g? Pause the video, think about it. Okay, what's your guess? Did you say not? Great. Right, this is neg b, written as a relation. And what I recommend you do is take a look at these criteria, right? These guys, or this guy, and just double check that these criteria hold for g that I just wrote. Okay, let's do another one. Oops, that's a little too blinged out. I said I'd like a black pen. Thank you. Okay, let's do the next one. We'll call this h. Take a second, think about it. Okay, how do you figure this out? Well, in this case, what we can actually do is draw a truth table, right? What's really going on here? These are inputs. This is an output. Okay, so if we wanted to draw the truth table, we would say something like this, right? So true, true, true. I1, I2, output. True, false, false. False, true, true. False, false, true. Oh, impy. Implication. Great. Okay, let's do a couple more. I'm going to do a couple on numbers, and then I'm going to do one on lists, and that'll be it for this video. Okay, I, J, and K feel like kind of funny names for functions, so I'm going to call this one L. Okay, this one's going to be infinite because there's an infinite number of nats, so I'm just going to sketch it. Okay, pause. What does this function do? Oh, L of 5 equals S5 equals 6. L of 7 equals S7 equals 8. L is the successor function. Okay, here's another one. M not a super formal definition, but this is another way that people will give functions as relations. Think about it. What is this function M? Run it on some examples. I really need to figure out how to play elevator music in the middle of one of these. But okay. M of 5, just by pattern, should be 4, right? M of 3 is 2. M of 1 is 0. And then we also said M of 0 equals 0. So this is pred, the predecessor function. Right? How might we write this if we didn't want to use the dot dot dots? We might say something like this. M is equal to the set 0, 0, union S of n, n for every n in the naturals. So I want you just to notice we do this to get that special case for 0. So we'll talk more about this special case. There's other ways to define predecessor, and we'll talk about partial functions in the next video. But we'll leave it here. Okay. One more function on numbers, and then we'll do one on lists, and we'll wrap it up. Okay, here's a function p. Okay, a little more interesting. We'll take two natural number inputs and produce a Boolean as output. Okay, I did this one extra mathy just to see how you like it. Think about it for a minute. Okay, let's look at just the true part, right? Because the false part, this is just a negation. So if we can understand the true part, we'll know what this function does. What's going on here? Well, we're saying that nm will relate to true, that is p nm equals true if and only if there exists a k, n plus k equals m. Okay, how might that happen? Well, we'll have a number line. Here's n, here's m, and we need k steps between them, k greater than or equal to 0. Aha! N is less than or equal to m. That's just a fancy way of defining less than or equal to. Okay, last one. Okay, making it fancy. Okay, think about this one for a second. Oh. Head. Really, I think head option. Okay, cool. Hopefully this has given you some nice practice just thinking about functions as relations. It's a really handy sort of mirror you can hold up to a definition to say, oh, I'd like to just think about this function as a set of pairs or a set of triples or whatever. And that often is a really nice sort of change of perspective that lets you understand the problem in a different way. We'll want to use this perspective a bunch in the sequel, right, when we go on to talk about accountability. So that's why we're starting with this now. Okay, more videos coming at you soon.